Hello students, welcome to Akshara 8 Foundation. So today we are going to discuss about the moment of inertia. We are discussing topics in rotational motion. In the last topic is synopsis 2, we have completed the torque, okay, and we have completed the numericals related to torque there. So today we are going to see about the moment of inertia. So about inertia we have learned in Newton laws of motion. Newton first law of motion, we have listened the term inertia there. Then moment of inertia is what? Okay, moment of inertia. So now today we are going to discuss about that and we are going to understand about the moment of inertia. So synopsis 3, moment of inertia. Moment of inertia. So in the last concept about the torque, whenever we are discussing about the torque, we have discussed about the torque there. So moment of force we have seen there. Moment of force. Moment of force is nothing but product of force and the perpendicular distance from the axis of rotation. Okay, here now moment of inertia. So whenever it is related to inertia, that is immediately there is a mass will be coming into the picture there. Okay, inertia, moment of inertia. Now here the product of mass and square of the perpendicular distance from the axis of rotation is said to be the moment of inertia. Suppose let us consider here a rigid body. So consider this is a rigid body there. It is an object there. So now this object is rotating about the axis there, about this axis. If this object is rotating about the axis there in anti-clockwise direction there, okay, in anti-clockwise direction if it is rotates, so then all the particles of the body, so this is, let us consider M1 body and here M2 body if we consider and M3 bodies if we consider there, this all the particles of the body up to here Mn particles of the body, the sum of all the particles is nothing but the rigid body, mass of the rigid body, sum of this all the masses is nothing but the mass of the rigid body now. So now each and every particle in this rigid body, there is a certain distance will be there from this, so this distance, let us consider it is the R1 distance and now here it is the R2 distance and this one will be the R3 distance and this is the Rn distance. So now this all the particles will be have the circular motion about this axis of rotation with the radius of the perpendicular distance between them. Perpendicular distance between them. Now, if we consider this particle mass of the particle, first mass of the particle here, that is m1. If we consider there, then the moment of inertia of that. So moment of inertia of that it is written as this mass will be from the axis of rotation about which it is rotating. It is there a distance of r1 and the mass is here m1. Now the moment of inertia is nothing but it is the product of mass and square of the perpendicular distance from the axis of rotation is known as moment of inertia. Okay. Suppose if we consider here that is the whole rigid body we have considered there. Now mass of the whole rigid body can be taken as here capital M. That capital M is nothing but it is the summation of all the individual particles up to n here mass, summation of all the masses of the individual particles of the whole rigid body there, that is nothing but the whole mass capital M. Okay, there is a capital M there now. Okay, so now the moment of inertia of that rigid body, the moment of inertia of the rigid body. So now he is this all the particles of the mass will have the center of mass in the body. The center of mass may be present in the body or outside of the body. We have learned in the last previous concept, in a previous chapter. No, the center of mass. Suppose here it may be present there. This is the center of mass of this whole rigid body. Center of mass of the rigid body. Now that center of mass, it will be at a certain distance there. Let us consider that RCM. Now the moment of inertia of that whole mass of the body can be defined as product of mass of the rigid body and the square of the perpendicular distance from the axis of rotation to the center of mass of the rigid body. Center of mass of the rigid body. So it can be written as here the formula. The moment of inertia is denoted by the letter I, that is equals to mass of the rigid body is product of mass of the rigid body and the square of the perpendicular distance from the axis of rotations about which it is rotating to the center of mass. That is the distance here RCM. So we can write here RCM whole square, RCM square, RCM square. This is the moment of inertia of a rigid body about which it is rotating there. About which it is rotating. And this is also equal to, so we can write here this I is equals to, even we can write there. Now the moment of inertia of this whole rigid body, it is equal to the moment of inertia of the individual particles of the body moving around a axis of rotation there, about the axis of rotation. Okay. So now the individual moment of inertia can be written as here I1 plus I2 plus I3, so on up to here we can add there IN. We can add up to IN there. So now then here this moment of center of mass, here we can add there this one. Okay. So moment of center of mass, we can add here m into RCM, m into RCM square is equals to, so this one we can add here m1 R1 square plus m2 R2 square plus m3 R3 square plus so on up to mn Rn square, mn Rn square we can add there, mn Rn square. Okay. So if we consider this, all the masses of the particles are identical. Mass of the particle m1 and m2, m3 and up to mn, if they are considered identical particles there, so suppose here m1 is equals to m2 is equals to, that means all the particles which we consider there, they are equal masses. If they consider their equal masses, so on up to here is equals to, so on up to, that is mn is equals to, we can write there m, if you write a small m then. So what happens there? So capital M into here RCM square is equals to, so m into R1 square plus m into R2 square plus m into R3 square plus m into R4 square, R4 square plus so on up to here mn into, so that is mn is nothing but again it is a m only, m into Rn square we can add, m into Rn square we can add. Okay. So now from this here we can add there capital M into RCM square is equals to, if you take here m common, here we can take m common now. So here m we can add there, m into, so R1 square plus R2 square plus R3 square plus so on up to Rn square, Rn square we can add there, Rn square. Okay. So now from this, if these all the identical particles, summation of m, we can add here n into small m, n into small m we can write now. All are the individual particles, they are equal to m there. So m plus m up to so on n times, then it will become, this capital M will become n into small m times it will become there. Now here we will be get here that one. So n into small m times of RCM square is equals to m into R1 square plus R2 square plus R3 square plus so on up to here Rn square, Rn square. Now here this m and m will be cancelled there, so we will be get here here RCM square is equals to, we'll get R1 square plus R2 square plus R3 square plus so on up to Rn square, divided by, here n will come there, divided by n. So now this square of the perpendicular distance from the axis of rotation to the center of mass, so that is said to be the radius of gyration. So the radius of gyration, here it can be RCM can be equal to K we can write there. K. So it is the radius of gyration. Radius of gyration. Radius of gyration. So radius of gyration is nothing but the perpendicular distance from the axis of rotation to a center of mass of the rigid body is said to be the radius of gyration. So that RCM can be taken as here K. So now that equation can be written as here K square is equals to R1 square plus R2 square plus R3 square plus so on up to here Rn square we can add there. Rn square divided by n. Rn square divided by n. So therefore the radius of gyration can be written as here square root of R1 square plus R2 square plus R3 square plus so on up to here Rn square. So this is a expression for the radius of gyration. Here K is this one, radius of gyration. Already given now. K is the radius of gyration. Radius of gyration. Radius of gyration. Radius of gyration there. Okay. So this is about the moment of inertia. Moment of inertia. This moment of inertia will be depend on, see, moment of inertia formula what we got there here, mass of the body and the square of the perpendicular distance from the axis of rotation to the center of mass of the body. Suppose if we consider the individual particle, product of mass of the body and the square of the perpendicular distance from the axis of rotation from about which it is rotating there. Okay. So mass into distance square, perpendicular distance square. So the moment of inertia will be depend on the mass and the distance from the axis of rotation about which it is rotating there. So this moment of inertia will be depend on the mass of the body and the perpendicular distance of the body there. It will be depend on mass of the body, mass distribution of the body and the perpendicular distance from the axis of rotation about which it is rotating there. How much distance it will be placed, based on that it will be depend there. Okay. So it is directly proportional to mass and it is directly proportional to the square of the distance between the axis of rotation to the point from where it is rotating about that axis there. Okay, that is the moment of inertia. The moment of inertia it is measured. See here the unit is what there? Mass and meter square. Sorry, mass is nothing but kg. Kg in the kg it will be measured and distance square. Distance square is nothing but meter square right there. So kg meter square will be the SI unit. Okay. So now the SI unit of moment of inertia I is kg meter square. Kg meter square. Kg meter square will be the SI unit. Now the dimensional formula what can we write there? Dimensional formula of I. Dimensional formula of I is, so kg will be denoted here capital M, m power 1, so L power 2 and T power 0. There is no T term no, so we can add here m L square will be the dimensional formula. M L square will be the dimensional formula. Okay. So next one we can see there here moment of inertia of the continuous mass distribution of object. Moment of inertia of continuous mass distribution. Okay, next one right on there. Moment of inertia of continuous mass distribution. Continuous distribution of mass. Continuous distribution of mass. Continuous distribution of mass. Okay. So suppose you can see there the body, rigid body we have considered there. So rigid body, the total moment of inertia we have written there here, mass of the body and we can add there k radius of gyration, k square. So m into k square we can add there, m into square. So suppose if the body is a regular shaped body, then we can get the perpendicular distance and this one mass, center of mass will get there and mass of the body we can get there. Okay, we can measure the mass of the body, and if you write here, we'll get the center of mass. But for the objects which are distributed mass continuously, whether it may be uniform or non-uniform, so continuous distribution of mass may be present there. Okay, so for that moment of inertia, how can we find out that? So this moment of inertia will be dependent on mass and the square of the perpendicular distance. Okay, and it will be dependent on the axis of rotation. So from the axis of rotation, how much distance the mass is rotating. So based on that, this moment of inertia will be present there. So mass distribution is different then moment of inertia can be written as here I is equals to integral of here we can write there instead of here this small body. This is the whole mass of the body we have considered there. Suppose if consider this is the mass of the body, it is rotating about this axis there, axis of rotation. Now if we consider a small mass of the body, so this mass of the body consider their dm mass, and this dm mass is at a distance of, let us consider r. Okay, consider of the dm mass is, and it is rotating about this axis with the radius of r distance. Now the moment of inertia of that body. So now the moment of inertia here di will be there. Moment of inertia about the dm mass will be di, we can write there. So now di is equals to here. So di is equals to, so di is equals to that we can write there here. So dm into square of the perpendicular distance. This is r square we can write there. Square of the perpendicular distance. Now if you do the integration on both sides, integral of di is equals to integral of dm into r square. Now here I is equals to, we know that integral of di. So integral of x d integral of dx is nothing but x will get there. So integral of dA is also will get there here I, and one more formula we will use here, integral of x power n dx. X power n dx is equals to x power n plus 1 divided by n plus 1. Okay, this is the formula we will use there. So now here we will get the integral of dm into r square, we can write there, integral of dm into r square. This is a total, and here we will write the limits from the mass, from where it has distributed, from which point to which point. Okay, so that limits will write here, this that mass is maybe here from throughout this distance it will be there. No, let us consider here the distance is r1, we consider there r1 to r2, we can write there. Mass has distributed between the limits r1 to r2 limits, then we can write there by using this any type of the for any body the moment of inertia we can able to find out there. So now we are going to see there the moment of inertia of a particular shape of the objects there. Okay, so now we will see there moment of inertia of a uniform rod, moment of inertia of uniform rod about the perpendicular to the plane passing through the perpendicular to the plane passing through the uniform rod there, center of uniform rod. Now here we can see moment of inertia of a uniform rod moment of inertia of a uniform rod about the center of rod, about the center of rod, about the center of rod passing perpendicular to the rod, perpendicular to the rod. Okay, so that is the moment of inertia we should find out there. So now I will show you the diagram how it will be there. So suppose let us consider this is a uniform rod of certain length here L, and length of this uniform rod is L, we can write there, and the mass of this is a capital M. Mass of this capital M there. Now we should find out, it is a continuously distributed mass. So how to find out the moment of inertia of that? About this point there, it is moving, it is perpendicular to this line there, perpendicular to the center. about this, what is the center of mass we can consider there. Okay. Suppose if it is center, then this distance we can add there here, the distance is L by 2 now here, we can add L by 2. So this distance will be L by 2 from this one, that is the origin, and this one will be plus L by 2. We can add this as a origin there, plus L by 2 it will become there. So now the limits we got there, mass is distributed from minus L by 2 to L by 2. Okay. So now if I consider here dm mass of the body there, so this is a small dm mass of the body. If this dm mass of the body is at a distance, consider at a distance x, at a distance x. Now x is vary from minus L by 2 to 2. So this, and if it is x distance there, we will get a moment of inertia of this part of the mass, we will get there di. We will get the di there. So now di is equals to what can we write there? So dm into x square, dm into x square we can write. Now integrate on both sides, and here this is mass is changing from where there, minus L by 2 to L by 2, minus L by 2 to L by 2 will get there. Now integral of dm will get here, integral of di is nothing but di, I only will get there. Okay, integral of di is equals to will get there I. So now here now integral of di is nothing but here I we can add there by using that formula. Now here the limits are minus L by 2 to minus L by 2 to L by 2 dm. Now so here we'll get there integral of minus L by 2 to L by 2. So dm value we should add there. What is the dm value we can add there? So dm value we can write it is, so like this, linear mass density, by using the linear mass density we can add there. So linear mass density lambda is equals to we can add there. So mass per unit length, this will be, even it is equal to the mass of this and the length. So what is this length here? X distance, no, x length x there. Okay. So here we can add there dm by here, how much length it is there, the mass is here x distance there. So now here dm is equals to what can we write there? So m by L into x, m by L into x we can add there, m by L into x. Here the what is this distance here, this distance of this one, distance of this one, see here we can add there, this is dm by dx we can add there, dm by dx, distance of this one, here also we will get there dm by dx, okay. Now here m into L by L into dx we can add there, m into L by dx we can add. Now here that value if you write there, in place of dm we can write it is a x square into dm is nothing but, so m by L into dx we can add there, m by L into dx. So now here I is equals to integral of minus L by 2 to L by 2, integral of minus L by 2 to L by 2. So here m by L x square dx we can add there, x square dx. Now m by L will be the constant, it can be taken out from the integration there. Okay, if it is taken from integration, so we can write like this, integral of, okay, this one I is equals to, so we will get here m by L, it will be common, and here integral of minus L by 2 to L by 2 is equals to here x square dx we can add there, x square dx. So now this is in, it is in the formula of like x power, integral of x power n dx, no, integral of x power n dx. So integral of x power n dx, what can we write there? Here x power n plus 1 divided by n plus 1 we can write there. Okay. Now apply that formula and we'll write the equation there. I is equals to m by L, integral of x power n dx means here x cube, x plus x power 2 plus 1 divided by 2 plus 1. So 2 plus 1 means 3 divided by 3 will get here. So here we'll get the lower limit is minus L by 2 and here L by 2 we can add there. Okay. So now here I into, so capital M divided by, so capital M divided by L into, here upper limit, first we should write upper limit and then next lower limit. So upper limit here L by 2 whole cube divided by 3. So minus L by 2 here, this one, minus L by 2, here we can add there, what there, L cube divided by, here 3 we can add. So now substitute here there, so I is equals to M by L, so here L cube divided by, this is a 2 power 3, 8 will come there, 8 into this is 3 is there, so 24 will come. So minus it become plus there. Here also it is L cube divided by, so 24 will come there. 24 will come there. So now what will get here now? That value I is equals to M by L. So that value here 2 into L cube divided by, so 24 we can add there. So this is 2 1 ja and here 2 12 ja, and L1 and this will be cancelled and 2 will become there. So therefore the moment of inertia of the rod can be written as here ml square divided by 12. So the moment of inertia of the uniform rod about the line passing through the center perpendicular to its length there, So this we can add here I is equals to ml square by 12. So this is the moment of inertia perpendicular to the rod which is passing through the center, about that it is rotating there. That means here we have seen now about this line it is rotating, about this it is rotating means, so we will get the final formula is I is equals to ml square by 12, that is the answer there. Suppose now if the body is moving, suppose if the body is rotating about the axis, so it is like this. If this uniform rod is rotating about the axis of the rod, about this it is rotating there, Now, so this is, if we consider that is L means this will be breadth now, we will consider their breadth there. So it will be started from minus b by 2 to, this is b by 2 will add there. So b by 2 will apply the same formula, then moment of inertia about the axis of the uniform rod, and it is passing through the axis of the uniform rod. Okay. So then here we will get there mb square by 12. This is a moment of inertia of the uniform rod which is rotating about its own axis. It is rotating about its own axis there. That is moment of inertia of the rod. Suppose next one, here we will be right there, next case, second one we can add there in that. So moment of inertia of so rectangular plane lamina. Okay, rectangular plane lamina, plane surface or plane lamina. About the line passing through the center, perpendicular to its plane, there. Suppose this is a rectangular, consider that it is a rectangular rod, and here it is passing like this. So about this line it is moving. That means it will be like this. So it is about this line it is rotating. About that line it is rotating. That rectangular plane is rotating about that line there. Okay. So now here we will have the length and the breadth there. So about this, the plane lamina is rotating about this means it is perpendicular to that, passing through the center. So we will write there So about the length. So the total moment of inertia can be written as moment of inertia about the perpendicular to the length, about the perpendicular length plus moment of inertia about the axis, moment of inertia about the axis of the rectangular plate there. So these two we should write there here. So from this we have got no moment of inertia about this rectangular surface, about this surface we got there ml square by 12 we got no here. So we will be get there ml square divided by 12 plus here ml square by mb square by mb, this is a b square, mb square by 12 will get there. This is a moment of inertia of the body. Okay, I'll write it there. So this is a moment of inertia of the rectangular surface about its length and moment of inertia of the rectangular plate about its breadth. Okay, so now here from the both the equations will get there I is equals to about the length it is ml square by 12 we got there plus about the breadth, if it is rotating about the axis then we will write there here mb square by 12, mb square by 12. So we can write here therefore the moment of inertia about the rectangular lamina perpendicular to its surface, it can be written as here m by 12 into L square plus B square, L square plus B square. So this is the moment of inertia of the rectangular surface. Like this, even we can find out the moment of inertia about the circular plate or ring, so disc. So that and all we are going to see in the next class. Tomorrow we are going to see the moment of inertia of the another rectangular surface of the body which are distributed continuously, mass is distributed continuously there. Thank you children, have a nice day.